Good day. Today we can discuss the topic about piecewise continuous trial function, solution for weighted residual in weak form. Here, why we need piecewise continuous trial function than normal weighted residual function? Yes, we can see. Generally, the derivatives can be differentiated it into two types, which one is strong form, another one is weak form. How can we get strong form differential equation and weak form differential equation? Because of its derivatives. So what is meant by strong form? Strong form is the conventional differential equation which solution must satisfy, and it follows differentiability requirements on the solution to the equation. So the derivative is continuous one. For understanding this, I can explain with some example. Here you see the function f of x is equal to x square is available. We can differentiate this x square with respect to x. From this we can get 2 into x, which is a normal derivative of x square. So this function is a continuous one. So these kind of equations are known as strong form conventional differential equation. So next we can move to what is meant by weak form. Weak form is an alternate representation of the differential equation. When we get the derivative as infinitive means we can get the weak form differential equation. So weak form must satisfy the solution in integral sense. It relaxes the strong form requirements. What I told you earlier, what is meant by strong form, which may have some relaxes with that condition. For understanding this weak form equation, I can explain with one example. Here you see f of x is equal to sine of 1 by x is the normal derivative. Here x should not be a 0. If for example, if I substitute 0 for x means I can get the sine of infinitive. Okay, 1 by 0 is infinitive, so that sine infinitive I got. So the derivative is infinitive. I can't get the exact solution. So these kind of equation is known as weak form. So finite element method, how can we solve this kind of weak form? Yes, for the reason piecewise continuous form is available. So the assumptions are, the first assumption, trial function solution closer to the exact solution, which means curve fitting. Here what is curve fitting? According to our right hand figure, you can see the red color graph line available and the green color graph line is also available. Here we can't get closer the green color line to red color line. So some unmatched curve is available. So which have poor curve fitting. So we can't get the exact solution. So with the aid of piecewise continuous trial function, we may get the exact curve fitting. So the curve fitting is best done with the piecewise. If more number of pieces available with the system means we can provide the best fit with the red color and the green color graph. After that, in weighted residual method tries to get exact solution from trial solution. So weighted residual method tries to get the exact solution with the aid of trial functions. So if the solution domain has more number of pieces means we can get the better fitness. Here you see I can split the domain it into 12 number of pieces. I can split the pieces it into n numbers. From this we can get the exact solution than approximate solution. And so piecewise solution method is used in weak form of weighted residual method. I can explain the same with some problems. Here you see one curvilinear graph available. In that x-axis is named as f of x and y-axis is x. In x-axis there are 10 divisions are available. In y-axis the curve occupies 2 divisions, which means 0.5 to 1. So here Now I can do the approximation with the one line segment problem. Here, how can we get the f of x value? F of x is equal to f of 0.5, because one line segment is started from 0 and ended at the point 0.5. So function of 0.5 is the our start point minus 0. 0 is the end point. F of 0.5 minus 0, and bottom parts in x axis I have 0.5 and 0. 0.5 minus 0 into the overall function is x. So x domain is x. So that into x, which can be represented as like if I simplify this, I can get f into 0.5 divided by 0.5 into x. So this function can be expressed as like f of 0.5 1 divided by 0.5 can be expressed as like 2. So that f of 0.5 into 2 into x. So this one line segment is started from 0 and ended with 1. Here I won't go for 0.5 to 1. I started from 0 and ended with 0.5. So I can't get the exact solution with this one line segment approximation. So that I can move this problem with the two line segment. Here you see the problem is started from 0 and ended with 0.5, and also I can introduce another line segment which started from 0.5 and ended with 1. So this problem can be solved by two line segment approximation. Already I solved one line segment approximation which gave f of 0.5 into 2x. What about the line is started from 0.5 and ended with 1, which is second segment? Yes, f of x is equal to previous point f of 0.5 plus the bracket, square bracket open, the start point f into 0.5 minus end point is 0 divided by 0.5 minus 0 into x into minus, x minus 0.5 I got, but the boundary condition is 0.5 less than x less than 1, which is the boundary condition available with this second segment. So which is the form of two line segment approximation. According to Seshu, the textbook of finite element method propose some techniques. What is four line segment approximation? Here you see the curve is available in the plot region. The curve can be split it into four line segments. Here you see the first line segment is started from 0 and ended at some more point which is named as 0.25, and the second line started from 0.25 and ended with 0.5, and the third line is started from 0.5 and ended at the point similarly 0.75, and the fourth line is started from 0.75 and ended in 1. So four line segment approximation is also possible according to Seshu. Here f of x is equal to f of function of 0.25, because the first line ended at 0.25, started from 0 and ended at 0.25. So the function can be explained as f of 0.25, and the f of 0.25 is started from 0. So that f of 0.5 minus 0 divided by where the point ended 0.25 minus 0 into the domain. This domain space is x, so that I can represent x, which can be solved is equal to the function of 0.25 into 1 divided by 0.25. What can we get from 1 divided by 0.25, which is 4. So that into 4x, but the boundary condition is the line is started from 0 and ended at 0.25. So the boundary condition is 0 to 0.25. And then what is the second line segment? The second line segment is started from 0.25 and ended at 0.5. So the boundary condition is looking like 0.25 less than x less than 0.5. So the f of x, the second line segment approximation, is started from 0.25. So that here I produced f of 0.25 plus square bracket. The second line segment is ended at 0.5. So that f of 0.5 minus the previous point. The start point of 0.5 is 0.25. So that f of 0.25 divided by 0.5 minus 0.25, which is here the 0.5 and here the point is 0.25, so that 0.25 into what is the domain space here, what is the domain, x minus the previous 0.25, subtract the total domain from 0.25, so that x minus 0.25 I got, which is the second line segment. After that, third line is also available. So what about the third line segment? Third line segment is started from 0.5 and ended at 0.75. So the boundary condition is 0.5 less than x less than 0.75. Here, how can I represent the approximation equation? F of x is equal to the starting point of third line segment is 0.5. So that f of 0.5 plus the ending point of third line segment is 0.75, so that f of 0.75 minus f of 0.5 divided by 0.75 minus 0.5. How I can get the start point of third line segment, I mean end point of third line segment is 0.75, so here I produce 0.75 and the third line segment is started from 0.5, so here I put 0.5 divided by the same 0.75 minus 0.5 into, I can subtract the total domain from these 0.5 points, so that x minus 0.5 I got, which is the third line segment approximation. And then fourth line segment, automatically now you can understand the fourth line segment is started from 0.75 and ended with 1. So the boundary condition can be represented as 0.75 less than x less than 1. Here you see how can I represent the approximation equation. F of x is equal to the starting point of fourth line segment is 0.75, so that f of 0.75 plus the square bracket, the end of the fourth line segment is 1, so that f of 1 minus the start of fourth line segment is 0.75, so minus f of 0.75 divided by the same point I represented here 1 minus 0.75 into the total domain is x and minus 0.75 is the previous one, so that x minus 0.75 I can get the fourth line segment approximation. I can solve this problem on numerical solution. Okay, here I consider one line segment problem with a curve. Curve may be composed with the equation of f of x is equal to sine into phi x by L as shown in this slide. And then the one line segment, what is the boundary condition? Here you see the boundary condition of one line is start from 0 and ended at 0.5, which can be represented, the x-axis always called as L, which we are also represented as L. So here what happened, L by 2, 0.5 means L by 2. So one line segment boundary condition x equal to 0 is one point, another point is L by 2. So the substitute first boundary condition, here two boundary conditions are available, one is x equal to 0 and another one is x equal to L by 2. So first boundary condition x is equal to 0 in f of x equation. So here in f of x sin pi x by L available, here I substitute 0 for x, so that sin of pi 0 by L I got, if sin 0 is equal to 0, so that f of x is equal to 0. Likewise I got, after that second boundary condition is x equal to L by 2. I can substitute same the second boundary condition in the sin into phi x by L. Here L by 2 is available, is sin pi L by 2 by L. So I can eliminate the L from the available equation as like this. I can simplify the equation as like sin pi into L divided by 2 into L. So I can cross L both denominator and numerator. So I can get sin pi by 2. Sin 90 always 1. So the f of x value is 1. Likewise we got the solution piecewise. Here you see the problem is available with the two line segment. I consider the same derivative function, which is f of x is equal to sin of pi x by L. So now I can solve this with the two boundary conditions. The same. Here you see the two line segments are available. The first line segment is started from 0 and ended with the L by 2, and the second line is started from L by 2 and ended at L. So the first condition is x equal to 0 and x equal to L by 2, which is the boundary condition available with the one line segment. After that we can move to second line. Okay, substitute first boundary condition, which is x equal to 0 in f of x equation. We can get 0 as like previous slide. Okay, if I substitute the second boundary condition, which is x equal to L by 2 on f of x function, we can get the sin phi into L by 2 as x place divided by L. From this we can get 1. Likewise, we can solve this problem. Pi into L divided by 2 into L. I can cross both the L with the denominator and the numerator. I can get sin of pi by 2. Sin 90 degree is equal to 1. So that the solution for first line is f of x is equal to 0 and the end of second line is 1. And the two line segment, second line boundary conditions are, the second line boundary condition is started from L by 2 and ended at L. So substitute first boundary condition and x equal to L by 2 in f of x equation. What happens? Yes, f of x is equal to sin of pi into x. The x is replaced by L by 2 divided by L. The equal to 0 already have in equation available, which means sin of pi into L divided by 2 into L. Likewise we got. Now I can cross the L of denominator and L of numerator. From this I can get sin by 2, which is sin 90 degree. I can get 1. If I substitute L, the second boundary conditions in the equation, in the f of x equation, means I can substitute x replaced by L, so that sin of pi L divided by L. Now I can remove L in both denominator and numerator, so that the sin phi I got, sin phi is equal to 0. So one f of x, when I supply the initial boundary condition L by 2, I can get 1. The second boundary condition L I substitute in the f of x equation, means I can get 0, which is the solution available with the two line segment problem with a function, which is the piecewise continuous trial function on a weak weighted residual method. Thank you all. If you are having any doubt, you may ask me through comment box.